So, in the first two lectures what we have seen, the first lecture we have seen that there is a standard VLSI flow for design flow for the digital VLSI circuit. So, we start off with specification, then we go for high level synthesis, then we go for gate level synthesis and so on. So, and then we told that in the first module of the course we will be mainly discussing about the high level synthesis part, in which case there will be a specification. Following that we will get what you say the architecture design or a block level design of the circuit. So, now in the next lecture what we have seen that and we also discussed that the main emphasis of the course will be to lead you to algorithms and tools which will help a designer to automate this design or get some automated implementation of his specification by different CAD tools and algorithms. So, that is the main focus of our course. So, in the next lecture what we have seen that in the next lecture that whenever you have to process some inputs or some specification by algorithm or a procedure, then it has to be represented in a formal way. So, in the case of circuit, so if there is a specification, so we have to write the specification in a formal language, so that it becomes unambiguous and everything can be normalized, or it adheres to some standard. So, we discussed about that there are several languages to do that. So, you can do it using Verilog, VHDL, System C, etc. And Verilog is a well known approach which is used all wide. So, we just gave some idea about the Verilog code, and then we have seen that CDFG, that is control and data flow graph, is a very well known formal model which can capture your Verilog designs and can be represented in a formal state transition type of a diagram using CDFG, that is control and data flow graph. So, that we have seen in the last two lectures. There we have given a specification. Now, from the specification we want to go for a high level design, and for that what we have to do, we have to first represent it using a standard format or standard or a formal model, so that there is no ambiguity and that it can be efficiently processed by some algorithm and so forth. Then next what? So, then we have seen that Verilog is a very good language or is a hardware definition language in which you can represent your specification, and from that we can convert it into a control and data flow graph, which is a formal representation of the specification, and then we can do lot of processing on that. So, what we will be looking today? Today we will be looking at transformations for high level synthesis. So, what is that idea? So, idea is that some the specifications, if you see, are written manually. So, after that all the processing starts with automated CAD tools, but the idea is that specifications are derived from requirements, like say I want to develop a calculator. So, you write a specification that I need adder, subtractor, multiplier and so forth, and if it is a business calculator, then you need logarithmic, exponential, factorial, etc. So, based on requirements you will write down your own specification. So, that is the manual part of it, and then the specification can be represented in some kind of a automated so formal model like CDFG, etc. So, which is again not a very automated process, it's a very automated process, and you can map your specifications to any formal model. So, there may not be much error in that, but you can understand that when the specifications are converted into RTL, when the specifications are converted into Verilog or VHDL, that you are representing your specification which were in general English or general notion in your mind. Now, you are converting it into some Verilog or VHDL, and which you want to convert it into CDFG and go ahead in the design flow. So, this step where you are writing the codes to represent your specification is fully a manual process, and we develop this specification based on requirement and our internal analysis. So, there can be lot of errors, or you can say inefficiencies, etc. in the coding. So, in this case today's lecture we will see what are the transformations we can do, so that your code, that is your specification, become more precise, or it can become more efficient in terms of hardware, etc. So, let me again re-emphasize that again in a C code. So, if you are going to write for a given specification, if you are going to write a C code, and again if there is some inefficiencies, etc., which is discovered later part when the product is in the market. So, always you can go for a patch, or always you can change your code a bit so that it becomes efficient and all. But in case of hardware, so once the specification has been developed, you have written the RTL, that is Verilog, for that, and then it has been synthesized and it has been fabricated, sent to the market. So, even if you find that there are some kind of inefficiencies, like there could have been some optimization, etc., they cannot be again redone, because hardware is once fabricated and then it is sold in the market. So, there is no step of any redoing anything over here. So, that is why here we should be very precise on what we are doing, and we should not be leaving behind, or we should not think that there can be if there is any possibility of any optimization in any point of time, then we should be able to take care, saying that that whatever optimization could have been possible or whatever error was there, we have to debug all, and as much as possible, and we have to optimize our code as much as possible before we go for the next level in the design flow, so that the design which comes out is coming out only once at a time, is once and for all. After that there is no modification possible in the after the fabrication has been done. So, what we have to do, we have to be very sure that the design is very much optimized, the error free and so forth. So, in the first step, when that is the manual part, that is the most risky part of the design, because all of the steps are more or less automated by CAD tools. So, there is not much risk or problem of errors, as in the case of when you are writing a specification and computing in mind what you want to do and writing a Verilog or a VHDL code for that. That is the place where the maximum errors can creep in, because that is a purely manual process. So, today we will see what are the standard ways of debugging, that is similar as in the case of C. You run your Verilog code with different types of test benches, that is the inputs, and see whether this operate correct or not. In the second module of the course, we will see that there are formal verification methods also, in which case you need not apply anything, but you can formally or mathematically verify that your design is proper or your design matches the specification. That is a formal way of doing it. But there are also some other steps that we will see today, like there is optimization steps. We should not call it errors. So, whatever today we will see are not errors, but you can do lots of optimization. Like if there are, let me give an example, many of the examples we elaborated in the lecture. So, like say for example, if you have 3 expressions like A equal to B plus C, A equal to B plus C and A equal to B plus C at different parts of the code, and you find out that A and B values do not change in between these codes and in between these instructions. So, you can always set temporary variable T1 which is equal to A plus B, and whenever you want to assign A plus B to some variable, you did not compute A plus B once again, you just apply T to this. So, this is one kind of an optimization. So, this is not an error, but it is a performance optimization. In this case, you will be having only one adder instead of 3 adders if you are having 3 repeated operations. So, elimination of redundancy is an optimization. So, in this lecture, we will be mainly looking at what optimizations are possible in the code which is written by a human designer. Okay. So, the first is the introduction. You already said that first step is high level synthesis. So, in high level synthesis we represent it as a control and a data flow graph, because it is one of the most widely used model for that one. Okay. Then we emphasize that Verilog codes are converted into CDFGs. So, that is an automated flow, but the Verilog codes are developed from the human specification. So, the way you are writing your Verilog code will decide on the, because that is the input to your all the CAD tool algorithms or the formal algorithms, the input is the Verilog code. So, if there is no optimization in there, or if you miss out, if you have some redundancies and all, so your circuit will be unnecessarily larger. So, we will be mainly emphasizing on the Verilog codes and CDFG models to see if there are some redundancies or some optimization is possible, etc. So, that is actually called transformation. So, we will transform our Verilog codes or we will transform our CDFGs, because CDFG is a formal model. So, it is very easy to see them and go for the transformations. So, you will see that this well known transformation if you are applying to CDFG. So, our code will be, we should not call it bug free, because we are not catching catch all the bug of here. We are actually thinking that our code will be optimized. So, it will take less hardware, it will be more efficient over here. Correct. So, what are the different types of optimizations or transformations we will see? We will see compiler driven transformation, flow graph transformation and hardware library based transformation. So, we will see one by one. So, let us start with the compiler based transformation. So, what is the compiler based transformation? So, if you have read about the compiler design in your undergraduate class, so you know that our compiler also tries to optimize your codes in the best possible manner. But again the difference is that even if you have missed your optimization in the C language once, then you can again redo it, because it is nothing hard coded or freezed at one time. So, even if the customer says that it is not optimized, you can again go for optimization. But still we do a lot of optimization even in the software level, because we want to give a good product to the customer rather than every time getting complaints and repairing them or optimizing them. But in case of hardware, optimization is much more a severe problem and more important to do, because once the hardware is fabricated, there is no chance anymore to undo anything and optimize it. So, what is the compiler based optimization? In compiler based optimization, what we try to do, you might have already read that we eliminate redundant elimination, redundant computations are eliminated, partial redundant computations are eliminated, we go for dead code elimination, etc. So, that your code becomes very efficient in that. So, the same stuff can also be applied at the hardware level. So, that is actually in a compiler based transformation. So, that same concept if you write this. So, we will do. So, as I already told, this code optimizing compiler based optimization, what we do, the code optimization a very important step by the compiler, because by doing this the code which is written by the human designer or human coder will be optimized in terms of performance. Okay. One very important is actually, so what is the idea? So, what are transformations? In this case, that is you are transforming code A to code B by doing some optimization or doing some redundant elimination, etc. But you should be very careful that whenever you are doing the transformation, there should not be any change in functionality of the code, because you are doing only optimization, you are not debugging, you are not trying to save any operations, you are not doing anything on that round, only you are trying to do some performance, so that your in the other way you are actually the code is executed in an optimized way, or your hardware requirement is less in case of VLSI, but the input output behavior should be remain the same. So, how can you go for code optimization? First you have to find out what are the where are the opportunity to discover code transformation, like if you have redundant expressions. So, they are actually opportunities to do that. Then you have to prove that the transformation can be applied safely at those sites. Now, what is that? Say for example, if you have in one step a equal to b plus c, after that a lot of codes are there, and again here you will have a equal to b plus, sorry, you have d equal to b plus c, then what you can say that a equal to b plus c, this you can also store in a temporary variable t, and now instead of d, if you write b plus c, you can write d equal to t. So, that is one place where you can apply the transformation, but if you want to prove that the transformation is safe, that means you have to say that this b and c, they are not overwritten at any point from this part of the code to this part of the code. If it is done, then b and c we have changed in the path, and if you want to again write back the old value of b plus c to d, that will be an error which will change the behavior of your code. But if you say that here you have applied a equal to b plus c, after that b plus c has never been changed throughout this code from this instruction to this instruction, then very safely you can apply the value of a plus b, which is equal to stored in a temporary variable t, to d. So, you have to prove that it is safe. Then ensure that, then I have to ensure that the application is profitable. Like in this case, a equal to b plus c, you are eliminating one addition operation here. In case of hardware, you are eliminating one adder. So, that is very good a profit, because you are saving some computation. And then actually you have to rewrite the code. So, in that case, you have to use a equal to t equal to b plus c, and then here equal to write d equal to t, something like this. So, the basic idea is that first you have to find out where optimizations can be applied, then you have to prove that the optimizations really do not harm, they preserve the equivalence level. That is what do I mean to say is that there is no behavioral change at that level, and then you have to ensure that the application is profitable. That is, you can do a lot of transformations, but they are not going to be profitable, they are going to harm you maybe. So, in that case you do not go for that, but if you find out that you can save some computations and something, so you can go about that, and finally you have to rewrite the code. Okay. So, that is actually the idea of the code transformation using compiler based optimization. So, what will achieve in hardware? You will achieve in hardware lower area, lower power, higher frequency, less computation. And in case of software, what you achieve by this? You get your it will take, I mean the code will be executed faster, it will take less time in the RAM and so forth. So, basically the philosophy is same, but only the performance requirement is different. Okay. So, now we will see one by one what are the compiler driven optimizations. So, first is actually loop invariant computation and code hosting. So, what is the idea? So, here the idea is, if you have a loop, okay, so some loop is executing every time, and then if there is some variable like say a equal to b plus c, and the value of b plus c do not get changed in this loop. So, b equal to something and here c equal to something happens, but inside this loop value of b plus c do not get affected. Then what is there? You are unnecessarily going in the loop, and every time you are computing b plus c, which is assigned to the value of a, which remains same. So, the idea is that why b and c are not changing inside the loop, then why you want to keep b plus c equal to inside the loop? What you can do? You can keep the loop a equal to b plus c over here, or just after the loop you can assign that a equal to b plus c, depending on some situations. So, what is the idea here is that? So, idea here is that if there is some variables or some operations which is in a loop, but the loop, the iterations of the loop are not affecting the computation of some variables or some operations in that, then why unnecessarily you want to repeat those computations in the loop n number of times, as many times the loop is executing? Better you bring those stuff out of the loop, so that the number of times the loop is operated is saved by the computation which is being repeated but having no effect. Let us see the example. Okay. So, whatever I am saying is actually written over in these steps. So, let us see the Verilog code. So, in the Verilog code we say that initially a equal to b star c plus d, that is the operation. Then we are saying that while a is greater than 0, a equal to a minus d, and you say that f equal to e plus b. So, what happens? So, this is a loop which will actually execute a number of times, and what is a? A is equal to b star c plus d. Now, there is a computation over here. So, what is saying that f equal to e plus b. So, you can easily observe that there may be some other computations here also, but if you just look at this computation f equal to e plus b, it has nothing to do or nothing is affecting in the loop which is executing a number of times. So, why unnecessarily I want to put f equal to e plus b? Unnecessarily I want to execute it n number of times, or I want to compute a number of times inside the loop. This is not worth it. So, what I can do is that I can either bring this computation down here. So, I can bring this computation down here, okay, or I can bring this computation out of the loop. So, in this case what happens? The value will be computed only once, the loop will execute and come out with the required number of operations, and we will be saving n a minus 1 number of times operating this addition. That is the basic philosophy. Now, we will see this. So, we have modeled this whole stuff in a control and data flow graph. So, you can see that first we had a equal to b plus c star d. So, equal to a b plus c star d. So, this you can see b star c plus d. So, B star C plus D. So, this is equal to B star C and this is D. So, you are getting this operation. So, that is equal to A. So, now there is a loop. So, you can see that is a comparison, this is a computational loop. So, if it is false you stop, if it is true then you have to decrement the value of A and again you have to go back. And inside this loop there is one operation which is actually saying that A F equal to A, so sorry this is a plus. So, A star F equal to A star E kind of a thing. Sorry, this is E you can say. So, what I am mean to say is that, so in this computation A, B, D are there and this loop is executing a number of times. So, in this case what is saying, I am computing F which is equal to nothing but A equal to F equal to A plus E whatever some computation. But the thing is that this computation has no effect in this loop. This you can very easily find out because E is being read and F is being written and nothing of this is being used to compute this one or this one in this loop. So, had it been the case that this computation is affecting this case or some other part in the loop, so you can figure out that this part is very important to compute in the loop. But if you can just see this inside this loop, this is your loop part of it and this is the computation in the loop. So, this guy is not affecting this loop anyway. So, what we can do is that we can bring it out and bring it in the top, because then we will be saving the amount. There can be some other computation which is not shown here for simplicity. There can be some other computations in the loop which may be affecting this way, like you can have a computation like some G is equal to A star 1 kind of a thing. So, every time A is being decremented, so the value of G is affected by the loop. So, or you can also say that G equal to A plus, sorry, you can also write G equal to A, G plus A. This also you can write. So, what is happening, every time the value of A is being added to itself. So, it is equal to A plus A minus 1 plus A minus 2 dot dot dot. So, this computation will be affected in the loop. So, that you cannot bring out of the loop, that is very obvious. But here if you see this computation is not having any effect in the loop. So, just you can bring it out over here. So, that is what is this transformation that has been done over here if you can see. So, they have brought this transformation over here. So, E F equal to E plus B or E star B whatever may be the condition. So, this is you are writing it over here and this is your loop. So, inside this loop you are not doing the computation. So, the loop is executing a number of times. So, by bringing or hosting this code over here, so what you are achieving, you are saving the number of additions here by a minus 1 number of times. So, this loop is executing a times. So, once you have to at least here. So, what is the amount of saving? A minus 1 is the amount of time you have saved. Okay. So, that is what I have written here. So, you can note that the computation this one, or I mean if you say this plus, or if you in this case it is a star. So, whatever is the case, so you can also say the star is loop invariant, because the operands E and B used in this computation to calculate do not change with the iteration of the loop. That is, value of E and B do not change in the loop. So, unnecessary, why you want to put it this one? So, this one start this one, you can put it before the loop, sorry. So, this computation before the start of the loop, actually this is called code hosting. So, what is the basic idea? So, basic idea is that, so if you have any kind of an operation whose values or input variables or whatever is computation is independent in the loop, then better is that you forget about whatever you are having over there. I mean if you find out that these computations are irrelevant in the loop. So, what is the idea? You take out those stuff and either put it before the loop starts, or you can better put it also after the loop starts. I mean anywhere you can put it depending on situation. So, that is actually we generally move it up in the code. So, that is we actually call code hosting. So, formally speaking, let us see what we mean. So, in this case the conditions required to determine loop invariant conditions, formally how do you go about it? So, in this case it says that, so if there is a operation like assign variable this one, operator 1, 2, this one is this case. So, in CDFG generally you will have this one, you will all have operation nodes, and for operator 1, operator 2 and operator 3 you will have the storage nodes, like in this case these are your storage nodes and these are your operation nodes, that is very obvious. Okay. Then what you have to find out that if I mean these guys and these guys are constants. If these guys, then how do you find out that they are loop invariant? So, if these guys are constant, like for example, if you have a loop and you are saying that something like say f is equal to 2 plus 3. So, it will be 2 and it will be 3 kind of a thing. Let me just erase it and make it clean. So, in the loop you may think that f is equal to 2 into 3. So, you can have 2 here and you can have 3 here. So, this is again a constant. So, obviously 2 into 3 is equal to what? It is equal to 6. So, unnecessarily why do I want to have a 6 over here? I can write directly a 6 in f. So, again the code can be brought out of it. So, what it says that if the operands are constant, then there is nothing to do in the loop, they are totally irrelevant to keep in the loop, you can bring it out. Okay. the computations that assign values to the operands are located outside the loop. So, that whatever computations assign values to these operations 1, 2, 3, 4 are outside the loop. That means what? So, any computation what was like say this is equal to a plus b, this is equal to d, this is equal to 2 star f, something like this. And but all these a plus b, d and f, they are all outside the loop and nothing affects, and a, b, c, d, e or f whatever are unaffected by the loop. So, that means what? Whatever these operations are, they are allocated values which is outside the loop. So, then therefore, if these values are assigned, these operators or operands are assigned values outside the loop, it is obvious that inside the loop their values will not be changed. So, if this is the case, then why do you want to unnecessarily keep these things inside the loop? Better also you bring this whole expression outside the loop. And third, the computations that assign values to operations are there is an inside loop invariant. So, there is a recursive definition you have said that the basic idea is that, so if you find out that these operands are actually something whose values do not change inside the loop. So, either they are constant, then their values will not be changed inside the loop. If they are being applied values like operand 1, operand 2, operand 3 etc. are assigned values which are outside the loop, then also their values will not change inside the loop. And also it may be saying that operand 1, say the operand 1 and operand 2 are assigned outside the loop, and operand n. So, you can say operand n is equal to operand 1 plus operand 2, then what happens is the recursive definition in the third case. So, these values of these two operands are assigned outside the loops, and they are again assigned being assigned to operand n. So, again obviously the operand n value will also not change inside the loop. So, the recursive definition. So, we find out that such a case in which case the operand values are not changing inside the loop due to any reason like n or like constants, they are assigned outside the loop, again they are being assigned by such kind of operation whose values are again assigned outside the loop, and so forth in a recursive manner you can define. Then you can think that these values will not change anything inside the loop. Therefore, they will not change anything inside, these values will not change inside the loop. So, better what you do is that you do not keep this such kind of operations inside the loop, better you throw it out, so you host it so that their values will be computed only once which is outside the loop, and then you will be saved from n number of so how many operations you are saving, in this case operator 1, 2, 3, 4. So, if there are n operators, so n into a minus 1 if your loop is running a number of times, so that many number of operations you will be saving. Correct. So, that is one kind of an operation. Second operation is called the constant folding. So, just like I said that if you have some operation 2 star 3, C equal to 2 star 3. So, as a designer you may write this by mistake, or if you may not be so much an experienced designer, but you may write like something like this. So, in this case what happens, we straight away require a multiplier. But if you have some kind of a constant like this, so what you can do is that better the tool can find out the value is 6 and directly you can assign the value of 6. Just like let us look at the example. So, in this case you have written a equal to Verilog, this is a Verilog code. So, you have written a equal to 1 plus 3. So, this is CDFG for that, and you can easily go and write about the constant 2 and write a. So, this may look, we are showing very small examples of code, so you may think it to be very trivial, but the case is that think of a code which is tens of thousands of lines of code, and they are written by different people, and then you are actually merging it to one and combining them into one by proper interfacing and all. So, if a person is developing such a big amount of code by a team, multiple people are involved and all, so such type of mistakes, or I should say some type of minor stuff maybe sometimes overlooked by the people, and then actually they lead to lots of optimization problems in the end. So, even if it is a very small code, as a very human being or a human eye also you can look it out and discover there is a problem, but if your codes are very large and very complex in nature, so such type of things can easily creep in and lead to problems. Now, that is why even all the techniques we are illustrating by small examples, because if you take very big examples here, it will be very difficult for us to understand and for us to speak out in a class and also show in this thing. So, basically the concepts are being illustrated over here. So, whenever if you take some practical example, or if you are going to the industry to work on this, so whenever you will get some large codes like this, so these concepts will be in your mind, so you will be less prone to make some such type of mistakes. And then even if there are some mistakes, there will be codes to tell you that this is the problem when you have to go for optimization. That means in case of transformation, the code there will be what are the CAD tools will do? The CAD tools will tell you that, hey designer, see this is a problem over here. So, here is a redundant computation, or here is a code invariant computation. Do you want to uphost it? If you say yes, then it will do the modification for you. Like in this case, you may say that you have designed a code like this. like this one, it may say that is a constant value. So, do you want to write it as a equal to 3 and then transform your code. So, this type of warnings will be given. So, there are some kind of errors and some kind of warnings. So, error means where there are code bugs, like you have forgot to move a percentage, you have forgot to give a semicolon and so forth. But these type of things are warnings. So, it may say that these are some of the warnings. You can look at the warnings and you can modify your code if required. So, that is what next is the constant folding. So, in the constant folding we have operation 1, operand, operation 2 and so forth. So, if all these are constants, then what you can do, or somehow you can also pre-compute them, like it can be also be like that, like C A equal to 2, then B equal to 3 and then C equal to A plus B. So, in this case what you can do is that if you find out that a value of A plus B is always constant, do not change anything like this. After that V value of A and B is nowhere used, or you can think that the value of A or B is never changed. So, you can say that you better remove this and make that A equal to 5 kind of a thing. So, that is pre-compute. You can, if you can pre-compute the value of some final expression, then you can do that. This is actually called constant. So, the expressions which are computations over constants always generate the same output irrespective of inputs. In this case, you can say that you fold your constants and make it one value and do this. So, you can, in this case you save an adder, sometimes you can save a multiplier and so forth. Okay. So, now we will go to the second level of third policy of optimization, which is called redundant computation. That is very simple, but actually we always make this type of a mistake. So, we will see first the example, then we will come back to the formal definition. So, somebody has written a code, then he is saying that C is equal to A plus B, and then after some time he is reading C equal to A plus D. So, in this case you may say that there will be no fool to write this, but actually do not think of a case like this. Think that there are the very big code in between, and after a long time he is also writing A and B. So, what happens in this case, say there is another 10,000 lines in between this. So, after writing this A plus B, then after these 10,000 lines you may have written in over a week or something like this. 10,000 lines means there are a lot of procedures in between. It may not be a flat 10,000 lines code, but there will be a lot of procedures, etc., etc., etc. Then procedure, modules and so forth. Then after say 7 days again you forgot that you have already computed A plus B once, and you could have reused that, but say again you are writing A equal to D equal to A plus B. So, there it can say that there is a redundant computation. But you have to also observe one thing, that this is a redundant computation if and only if nowhere in the 10,000 lines of code A is here and B is here, nowhere you have assigned A or B new value. This should not be possible. So, you have written C equal to A plus B. Then after some 5,000 lines of code you are writing A equal to something, B equal to sometime, and again you have reused the values and all. So, after that if you are writing A plus B then equal to the same C, then you will be in a big problem, because that may not be true. But if it is the case that A and B equal to A and B you have written as A, and there may be some, you may think that A and B are some constants which are taken as inputs, may not be constants, but they are always taken as inputs, and then you do not change them, like they can be in the multiplier and the multipliant which you never change. Then after 10,000 lines of code, never you have assigned any new value to B and never you have assigned any new value to A. So, these things are not there. Then what is the case? Then obviously the value of A and B has not changed, and you could have very easily written D equal to capital C. Okay. So, but now it is very easy, but here is one line just after the answer. So, nobody will write like that. But if there would have been a practical case, consider a very big chunk of code here, there is a very high chance that you may forget what you have written in case of D equal to A plus B. So, you could have written D equal to A plus B again, and that is a redundant computation. Then what do you actually do? So, in this case this is the transformation and this is the transformation. Transformation is very simple, A plus B equal to C, and D you can write it over there. But you have to be very careful that the value of A and B should not change in between these two expressions. Okay. So, that is the operation A and B should not have changed between A and D. So, therefore, actually the compiler will tell you, or your tool will tell you that is a redundant expression, then you have to go and think about that whether you have changed, or you can search and find out whether, advanced tools can even tell you that whether you have A and B have changed over here or not. So, if there is no change of A and B, then you can go for this redundant computation elimination. Now, what is the formal way of doing it? The formal way is saying that assigned value is equal to operation this one, operator 1 this one dot, and assigned variable 2 is this one. Now, this one should be equivalent to this one, this should be equivalent to this one should be equivalent to this one. Similarly, all the operators should be same, all the operand and operand should be same. As well as that, nowhere after this expression, nowhere operand 1 1, operand 1 2, operand 1 3 dot to operand 1 n should change in between. So, that is the values of operand 1 2 3 4 5 6 n should be intact from this expression to this expression. Then only you can say that this expression I will store in a temporary variable and I will apply it here. So, that is actually the idea of redundant computation elimination. In other ways, say that we compute some expression and after that the expression do not change. Again, why do you recompute the expression? Better use this expression once again. That is the idea of this redundant computation elimination. But we have to be very careful here. Why? Because you are using A equal to sorry, you are using A equal to B plus C over here. So, C equal to A plus B over here, then you are again reusing that. But anywhere in this middle of the code, if A has been changed or B has been changed, then you will be having a very big problem, because in that case you are instead of A equal to B plus C, D you will be writing as C, or you may be storing it in some temporary variable and you will be writing it over here, and then you will be in a very big problem, because some other values will be assigned. So, in the course of optimizing your code, you may lead into erroring bugs. So, here in this case you are writing D equal to C. So, that case is also very risky, but then you have to be also very careful that A, B and C do not change over time. So, sometimes what people do, they put some temp variable like temp1, and then they will write D is equal to temp instead of writing D is equal to C, because A, B and C are user variables. So, it is very, very possible that user will be always using them. For different kind of assignments, etc., etc., etc. So, but if you are using a temporary variable, then you know that I will not be using that anymore. I will not be actually taking that, because they are already defined for compiler optimization. So, what happens is that you start with initial begin, then you say the temp equal to 1, correct, then temp equal to A plus B, then you know that value of A plus B is not changed. So, even if value of C changes anywhere in the code, you are not bothered. So, D equal to temp 1, you can write happily, and you will be done with this one. Okay. So, now this was about what you say is that redundant computation elimination. Now, we will go for a sub case of this one. So, for example, if you have a very big expression like A equal to B plus C plus D plus something, and again you have something like that. But now you can say that partially they are equivalent, like say for example, we will take an example over here. So, in this case you see here somebody has done a very long code over here. Now, you see D is equal to A plus B plus C and F is equal to A plus B plus C. Assume that there is a very big chunk of code over here. Okay, so, now you see in this case D and F, the whole expressions are not equivalent. But what is equivalent? The equivalent part is A plus B and A plus B. Only these two parts are equivalent. Still you can also save something, provided that A and B values do not change in this part of the code. They are assuming that they are not changing. Then what you can say, that I can say that D equal to A plus B plus C, then I can add one more step here, then T equal to A plus B, I can say that is my temporary variable. Now, here instead of A plus B, I can put the value of T over here. So, it will be T plus E. So, in this case, the saving will not be there as much, because obviously the saving is there, because you calculate A plus B, then you apply D equal to T plus C, and in this case also you apply T plus E. So, instead of 1, 2, 3, 4, so it is something like that, it will be temp equal to A plus B. Now, D will be equal to T plus C and after that F will be equal to T plus E. So, now you see 1, 2, 3 multipliers adders you are requiring, but in this case 1, 2, 3, 4 adders you are requiring. So, you are saving one adder in this case. Okay, but again, so like the previous case, you have to be very, very careful that the value of this is the part you are using for redundant computation, redundant sub computation in this case you are saying are equivalent. So, you have to be very, very careful that the value of A and B do not change in between this one. So, that has to be very carefully this thing. So, what is the formal stuff? So, if you have some expression like this, some expression like this, then you find out a sub part of it, like say operand 1, operand 2, this part is equivalent to this part, or this part may also be equivalent to a sub part over here. So, those things you can use it, that means this part you can save in a temporary variable T1, and now you do not compute it again here, use the value of temporary variable 1 over here. But you should be very, very careful that operand 1, 2, 3, 4 or whatever you are here, and between these two codes where you are applying the equivalence should not be changed or assigned anywhere in this case. So, if this is like very similar to the case of common sub expression elimination, but in this case it is not the full expression, it is only a part of the expression. So, just like looking at this code, if you see it is equal to A plus B plus C, and in this case again A plus B plus E. So, there are two expressions. So, in this case you can see that this part was common, like this part was very common. So, if you just look at graph level stuff, so it is very easy to traverse the graph, and you can find this is equivalent to this, this is equivalent to this. You can go for graph, some kind of graph isomorphism kind of algorithm to find out that subgraph isomorphism, that these two graphs are equivalent in nature. So, you can use them, and then it also writes, it is to be added to B over here, and it has to be added to F over here. So, in this case the operand in C, this case the operand in, this part is a different part of it. So, you can very easily go for common sub expression elimination. Okay. So, till now we have seen about how many we have seen that loop invariant, and hoisting, then we have seen some expression elimination, and then common full expression elimination, then also we have seen constant folding. Another very important thing we always hear in software is called dead code, and many times our code has some dead code computation. So, what is a dead code computation? Dead code computation in other words says that you have written a very large code. So, some of the expression you thought that this may be a very useful expression, I want to do something like that, but after that you might have realized that okay, these variables are not at all required, or this computation not at all required, but then you forget to remove it or remove those some parts of the computations which are not at all affecting your code. They remain still there because you thought of your logic as something, then you start writing your code, then after some time you find out that this logic is no longer required in your code, and you are not that important. So, you don't use them at all in your code anymore. So, but it still remains there because the very big code you forget to go back and exactly eliminate which part of the variables or which part of the computations you thought to be used, but are not required anymore. So, you could have gone there and eliminated, but it is a very difficult problem, because in a very generally speaking, if you may write some expression and then you can do a lot of computations, but you can find out that computation becomes a tautology. Tautology means it will be always true. Like you can, there is a very complex Boolean expression you can think this is true if a man goes to heaven, then if he tells the truth, then something happens, and also very big, say you are writing a logical code, and then what happens is that you can find out then based on all the input cases it will be a tautology, that is always between the answer will be always true or it will be always false kind of a thing. So, in that case you do not require such a big computation because answer is always 0 or always 1 kind of a thing, but it is very difficult sometimes to even prove mathematically or for a human being to find out that this is always the case, that is always true or false, that is the case is redundant, you need not go for such a computation, you can directly write 0 or a 1 in case. So, and sometimes you may also find out that whatever you are doing, say something you are doing as a very big expression and 0. So, that means it is of no importance, you should not end it with 0 because ending with 0 has no meaning, but that some computation will always lead to 0 and you are ending with something, that may be a very difficult mathematical problem to find out that in what conditions it will be there, and then prove that for all possible input conditions it will be a very predefined values and it will not change, or it is always 0 or 1, always true or false. So, that means dead code means a code which is lying inside your code, but is having no impact on your code, it is always either giving true result or always giving a false result kind of a thing. So, finding out such code in a very generalized environment is a very difficult problem, but and again it is always, therefore it is, I say that always if you are writing a code as a human being, we sometimes write codes whose values are always constant or whose condition results are always constants, and I mean we could have easily done away with this code. So, such type of codes can be thrown out of your main code which you are submitting for design if they unnecessarily lead to area overhead, etc. Like in this case I will tell you. Okay. So, you have a plus b, some people have written a code. So, initially they are saying that a equal to b plus c plus d, okay, and then he has written a equal to a plus y. He might have been the case that he might have thought that E is another output, in the case he might have thought. So, in this case his output should be, I mean what you call, so output is A, and also he could have thought that E is on another output, he might have thought, and then he have written this line E equal to A plus 1, but then after some time he might have changed the specification and he found out that the output is not at all required, no, that output A is enough output, second output is not required. So, he have eliminated the value of E, but he has actually forgot to do this, but then still he has defined register AE. So, he forgot to, I mean remove this definition. So, A is remaining a variable in his case, but it is not an output. So, he has just eliminated that E is not required to be output. So, he eliminates this here, and also as the output A, E was there, he also eliminated it. But another definition that we states that is a variable, he might have forgotten to eliminate, and also he might have forgot to eliminate A equal to A plus 1. So, this code unnecessarily will be in your computation, and it will lead to an adder and a register for E, and it will be unnecessarily hanging and making your area overhead. So, you can actually eliminate this part and you can eliminate this part. This is actually called a dead code elimination because it has no effect on the output of the code. So, like this, for example, you can have a look at it. So, this is the input and output. So, this is your output. This is not at all output, but still, so this part of the computation is not required and you can throw this out. So, dead code elimination actually talks of eliminating such a code, but actually it is a very simple example. So, you can understand this, but sometimes it may happen that there is a lot of condition over here and you are comparing it over here. Okay, now it may happen that, and this may also be if this is true, then you execute something, it may be the case. But as I told you, it may be computation here may be a very complex stuff, like if A then this, then so forth, not this, then, and you can find out that for all input cases the value is always going to be 1. So, and say you are comparing it with a value of 1. So, you are saying that if this is 1 and then the output of this one is 1, that is true, then only you do something. But you may find out that either because of the lot of input, all possible input combinations and whatever big complex equations you have written, always the values will be 1 or always the value will be 0. So, the answer is always true or always false. So, this is very well known. So, you need not go for such a big computation and a comparison. So, you can throw out all this and you can write the value as true and false. So, this is actually a dead computation, but still it is very difficult to find out the dead computation. because it is having no effect on your code, it is just saying 0 and a 1. So, like ending with a 1, ending with a 0 or ORing with a 1, basically it does not have any meaning. So, in such cases, to find out those parts of the code and eliminate it is very, very difficult. So, in this case was a very simple example. So, you can easily find out that this code has no effect on the output, but really to debug and find out that this logical part of the code is having no effect on the output is a very, very difficult problem. But still, I mean, we are always thinking of how we can minimize our code or how we can throw out the part which is not required, so that you can get a very good, what do I say, is a very good transformed code, so that it is, I mean, you get a very good, what do I say, a very optimized, I mean, argument for this, like, because code hosting, common sub expression elimination, actually you will save some part of your code. But if you can find out that very big chunk of code or very big module of the code is dead, it has not have any effect, or the effect is very redundant kind of a thing, or unnecessary, like ending with 0, ending with 1, ending with 1, ORing with 0 kind of a things you are coming into picture, then you could have thrown out this code, because this code is having not any effect. But that is actually very difficult to do and a difficult problem to solve. So, still people are finding out tools to find such portions of the code, give warning to the user and so forth. Okay. So, these were all about compiler driven transformation. Now, we will see some graph flow based transformation, that is, we have drawn this, what you can say, we always have drawn our this control and data flow graph. So, now what we do, now by looking at the graph structure, how can we optimize our code? So, that is actually called the flow graph transformation. So, two will see, that is actually tree height reduction transformation and is control to data flow. This already we have seen in the last lecture, that if you convert your data from control flow diagram to data flow diagram, CDFG, then you can save some redundant elements. Now, let us see. So, first we will go for this heist reduction, and then we will see what is the theory behind it. Okay. So, say for example, you have a computation like this. So, what is the computation? Computation is equal to A plus B plus C plus D plus E plus A. So, very long computation, this is your example, right. So, it is a very sequential kind of operation. So, let us just look at CDFG. So, this is CDFG. First you do A plus B, this result, then you go C plus D, then that result you go to OD5 and so forth. So, in this case, how many adder you require? So, in this diagram you do get 1, 2, 3, 4, 5, 6 adders are required. But in fact, you can also do it in one adder. How? First you do A plus B, store the value somewhere. Same adder you go for T, that is the temporary variable for A plus B, then what you do? You take the value of T and add the value of C, same adder, then you make it say T1, then the T1 you store somewhere, and the same adder you reuse for adding T1 and D and so forth. So, you require only one adder to do the problem, for solve the problem. But in this case, you require how many steps? 1, 2, 3, 4, at least 5 plus 1, 6 steps you may be requiring to do your solve your problem. For first step, these 1, 2, 3, 4, 5 additions are there. So, at least 5 steps you will be 5 additional steps you require to solve the problem. So, this actually the tree height is very, very large. So, now what we can do? We can go for some type of optimization, in which case we can say that we will have multiple adders, but we can do our operations in a faster way. So, here what we are optimizing? Here we are optimizing speed at the cost of area. So, we are giving more area and we are saying that optimization is possible. So, now in this case what we are doing? So, in this case see, we are doing A plus B in one go, C plus D in one go and E plus F in one go. Then we are adding the value of T1 plus 2, these temporary variables, that is in the another step, and the third step we are adding the value in this one. So, how many adders we have put? 1, 2, 3, 4 and 5. So, in this, all these 3 you require 3 adders for this one, this we are doing in parallel, and then one adder here. So, the same adder you can use, and again the same adder you can be used for this one. So, in fact, you are having 3 parallel steps. So, A plus B, then C plus D and E plus F, we are doing it together. Then one of the adder you are using for adding intermediate values for this one, and the same adder can be used for doing this one. So, 3 adders are required. So, in the previous case 1 adder was required, now you are using 3 adders, parallel adders, and you are doing the operation in 1, 2 and 3 steps you are getting. Your answer in the previous case it was a 5-step answer. So, again the tree height has been reduced from 5 to now reduced to 3 steps. So, what essentially we have done? In this case, for some very big expression or very long expressions, if you are using a single tree to do that or a very long tree to do that, the hardware requirement will be less, but in that case a very sequential kind of operation, and your time taken will be as many number of operators are there. So, that many number of steps will be required. But now if you can parallelize it, that is you are reducing the height of the tree, then you are taking more hardware, but you are now optimizing on the number of, what do I say, you are optimizing on the number of steps or the time required to do. So, formally what it says that tree height reduction is based on transformation that uses commutative and distributive properties and so forth. So, let there be an expression, okay, like we say that variable 1 then operator 1, then this so and so forth. So, this is a very very long operation as you can see. So, now what we can do, so if you go on sequentially from this, then what happens, it takes a very long time and the tree length is very very large. So, what we can do, we can break it up into sub-computations and then we store their outputs in some temporary variables, that is the idea. So, you have a very long expression like we say a plus b plus c plus d plus something. So, we are breaking them into b plus c, d plus c, e plus f and so forth and store their variable in temporary variables. So, the sub expression you are breaking it, this one and this one, you are operating in parallel. So, then again these two temporary variables, the output will be again here and again the output of these two other variables will be at, and then this can be also happening in parallel. So, what is the idea? Essentially the very big expression, you take 1 and do about it. This is one way of going about it. The other way is that you break it up into small sub expression and do that parallelly. Then store the intermediate results. Again you process whatever is possible in the intermediate results parallelly, and again you redo this thing. So, you can reduce the height of the tree and you can also get a very quick solution for this one. But what is you are losing? You are losing the amount of time. So, time loss in this case is very time gain is very high, but you lose in the area, because now whatever you are parallelizing, because you are breaking it into sub expressions. So, sub expressions you are breaking or whatever sub expressions you have broken up and you are eliminating and you are executing in parallel. So, that many amount of hardware is required. So, in this case 3 adders, 3 additions you have brought down into 3 sub expressions or 3 sub additions. So, 3 parallel adders are required, but now in the second step you can reuse any one of them, in the fourth step also you can reuse any one of them kind of a thing. Sorry, second step and third step you can reuse, but in this case in this long tree long height tree you are using the adders one after another. So, the storage space or the variable requirement is this adder requirement is very less in this case, and 1, and in this case it is 3. So, if you go for tree height reduction you will get faster operations, but what you will lose obviously your time you are gaining and you are losing in the area. Okay, so, that is about the tree height based transformation. So, next one is actually control flow and data flow based stuff. So, already we have discussed in the last lecture. So, we had some based on some conditions, you either do this computation, either you go for this computation, either you go for this computation. So, this is a control flow based representation. So, given a very log code, it can be a hardware definition language, it can be directly transformed to this one and you are going to get your solution. Okay. But then we say that if that is this CDFG can be directly obtained from your Verilog code. Okay, that is actually control flow based. Already this was illustrated in the last class, but now you see there is a lot of redundancy like BC are already there, then this D is already redundant, and then we showed that if you can go for a control flow based diagram or control flow based CDFG, the problem is solved. You read B once, you read C once, you read D once, and then you do the computation, but you forget about all the redundancies, you eliminate redundancy like B plus C is here once and B plus C is here once. So, so B plus C and B plus C, that is B plus C, you can see this is this is B plus C. So, this is computed once, used here, as well as it is also used here. So, 2 times it is used. So, if you go for a this is your control flow, and this is your this is data flow, this is data flow, not control flow. This is data flow based representation. So, already we have seen. So, in this data flow based representation, redundancies are eliminated, but again what is the difficulty we saw, that there is no one-to-one representation between the Verilog code and a data flow based representation. So, what we have to do, we have to go for flattening of the code, and we have to go take some tool or do manually redundancy elimination and so forth. But still your representation is better, area requirement is better and so forth. Okay. So, this was about your graph based transformation. So, which can lead to either a very fast action, or your hardware will be very fast at the cost of more number of hardware, or in this case you are reducing the redundancy like the control and data flow based stuff, you are reducing the redundancy and you are making a very compressed representation, but at the cost of you have to go for manual intervention, because in data flow based CDFG Verilog codes or HDL codes cannot be directly mapped. If there are nested loops and also you have to go for flattening and all those things that we have already seen. The third type of transformation is hardware library based transformation. So, what is that? So, your library has some kind of special gates. Okay, or what is the design library? So, if you want to fabricate your circuit, so you should have a library, like I have a 2 input AND gate, I have a 3 input AND gate, but you may not have a 100 input AND gate, but some of the expression may be like I1 dot, I2 dot, I3 dot I100. So, you can think that I will have a 100 input AND gate and my operation will be done. So, in digital design sometimes we have seen that our digital design are implemented with a 10 input AND gate, but in a real case a design do not have such a huge number of AND gates and all. So, So, a design library is given. So, people who are studying about fabrication and all, they know that it is very difficult to fabricate in VLSI gates having more than 4 inputs. Then the gate is slow and several other problems are there. So, that you can read out in any standard VLSI the digital design books, the CMOS design books, what is the problem and all. So, just take for me time granted that designing anything of more than 4 input AND gates or 4 input any kind of a gate is a very difficult problem. Okay, so now what do you have to do? So, what is the design library? So, design library will tell you that I have 2 input AND gates, I have 3 input AND gates, I have OR gates, I have flip flops, etc. This is the speed, this is the area and etc. So, all the definitions are there. So, you can also have some special stuff like you can have an incrementer, you can have a comparator, you have a multiplexer, you have carry forward adders. So, you say that I build some very good design blocks which are actually fast, take low power and very generalized. It may not be, it should not be very specific, but generalized like a flip flop, a multiplexer, a register, a comparator, which every people use, flip flops, etc., which is very commonly used, so that I can say that this is my design is very good, so better keep it in the library so that any person can use it. So, that becomes a design library. So, sometimes based on this design library some transformations can be done. Like for example, if I say that I want to compare a 6-bit number with 0, any 6-bit number is compared to be 0. So, how can you do that? So, you can use a comparator. So, it is very simple, if you have to use a comparator. So, this is your number 0 and this is your 6-bit number which you are taking, and these are all 6-bit zeros. So, this 6-bit number you want to. So, if it is all zeros, then you get the answer as 1 and so forth. Another very simple way of doing it is as what? You connect all these 6-bit numbers, all the 6 bits of your bus to a OR gate. If everything is 0, then you get the answer as 0. So, make it an OR gate. So, if all the input bits of the 6-bit number is 0, then you get the answer 1 and so forth. So, very easily you can say that a 6-bit NOR gate is a comparator for 0 of a number. So, if all bits of a number are 0, then the answer is 0, then the number is 0. So, if you feed a number all the bits of a number to a n bit, what you can n bit number to n bit NOR gate. So, if the output is 1, then you know that the number is 0, else it is not. But for that your design library should have a n input NOR gate, or you should be able to take some gates and make it as a 6 input NOR gate or whatever n input NOR gate kind of a thing. But otherwise, if you do not have such a kind of a NOR gate, say for the time being just say that n input or 6 input NOR gate is not available, then what you have to do? You have to take a comparator. Say comparator is available in the design library. So, you take a comparator, feed the 6-bit number, feed the value of 0. So, if the number is equivalent, then you will get 1, else not. But if your library has say a 6-input NOR gate which is specially designed as a comparator, then you will be very happy that you can use this. So, what is the better thing is that if you use a comparator, then comparator actually uses a lot of XOR gates for computing. So, that means what? So, if you want to that this that is say 2 3-bit numbers are there, say this is A0, A1 and A2, and say 3-bit numbers B0, B1 and B2. The 2 3-bit numbers, they have to be compared for equivalence. So, what you do? You have to XOR A0 with B0, A1 with B1 and A2 with B2. If all the XOR values are 0, that is both of all the bits are individually equivalent, then only the answer is equivalent. So, a comparator will actually involve all XORing with all the input bits that you have already learned in digital design undergraduate course. So, a general comparator will have, for if a 6-bit comparator, then you require 6 XOR gates to do that. But if you want to compare with 0, then you do not require so many XOR gates. You can easily take care of a NOR gate and solve the problem. But for that, your design library should have the specialized NOR gate which can compare with 0. And comparator with 0 is very much required in most of the cases, a very general purpose circuit, because if you implement a loop, then we say that for I equal to 1 to n, or sorry, you can say that for 0 equal to, for some value equal to 0 to n, or you can say that from n to 0, anything you can do that. So, many times we require comparison with 0. So, it is a very, you can think to be a very generalized block which should be placed in the library. So, if your design library has a comparator as well as a 6 input NOR gate kind of a thing, so you can change your simple comparator, and you can instead of the comparator you can bring in this stuff, right? Bring in what stuff? You can bring in your 6 input NOR gate for a comparator. So, that means what, based on something available in your library, you can always go for some kind of optimization. Let us take another example, like say for example, if this is a CDFG where you have one operation, you say that b equal to b plus 1. So, what is the one thing you can do? You can take an adder and you can do that. Okay. So, that is one stuff, but inside, but actually there is something called incrementer. So, it just the hardware is very simple. If you can go to the digital design, I mean what do you call undergraduate course, so you can find out that incrementer is nothing but it increments the number by 1, that is it. It is not of anything, it does not do any kind of full addition and all. So, there is no kind of full adder or half adder business involved there, it is just a simple circuit, it may increment the value by 1, that is it. Incrementing the value of 1 sometimes is also required in computing 2's complement and so forth. So, many times you have to add only 1 to a number. So, in that case this is called an incrementer. So, if in this, if in your library, design library you have an incrementer, so do not put a full adder over here, you just put an incrementer and our circuit will be smaller. So, this transformation is possible if and only if you have an incrementer in your library. So, this transformation or this betterment in your design is possible based on some hardware which is available in your library. So, they are called library based transformation. We will take another example like say multiplication with a 0. So, you have a computation like b equal to a plus 2. So, you always know that multiplication by 2 is nothing, you should not put a multiplier because multiplier is a very complex hardware, and multiplying by 2 is nothing but you have to go for a left shift. Like for example, if you have 0 0 0, you want to multiply it by 2, it will be 8, so it will be 0 0 0 1, you go for 1 bit left shift. So, if you have a left shifter in your library, so instead of putting a multiplier you go for a left shifter here. So, in this case your hardware will be less and you will be optimized, but this is possible only if you have a left shifter in the library or you have to design it and put it in the library. So, this type of transformations are possible only if you have a what you can call some specific stuff in your library and which is helping you optimization by not using a general purpose comparator or general purpose multiplier, general purpose adder is not required. For some specific cases some other circuits are available which you can use it. So, this was about all the transformations possible, and as I told you, this is the manual step you write your code before going into automated CAD tools which will be dealing in the next lecture, that once you say that your design is complete, it has no bugs or every transformation has been done, the code is very optimized, you then go for automated tools for high level synthesis, gate level synthesis and so forth. But this stage as it is manual, so you have to apply all these transformation techniques, debugging techniques etc. Debugging techniques you will be looking more details in the verification module of the course, but very manual or a very rudimentary kind of debugging is you apply some input patterns and see everything is proper or not. So, once everything is done, then you can go for design of what you can call high level synthesis, that is from this Verilog or CDFGs we will go for a block level architecture of the circuit, that we will be seeing in the next module of the course. But here it is very important because the codes are written manually, so you have to go for transformation so that you get optimized stuff in all respects. Okay. So, before we stop we do the question answer code, question answer session. So, it says that the question is say it is a simple question like after transformation of the CDFG code, what is required, why it is required to pre-process them through high level synthesis. So, what step is required before pre-processing? Just like I was saying that after you transform CDFGs and HDL codes to some automata like what you have already done, we have taken HDL code like Verilog and we have made it CDFG, then in the next module we say that we will be processing them to high level synthesis tools. Then what step is required? So, there are two things as I said, HDL and this type of codes are transformed, it needs to be verified that the input output behavior remains the same, that is you are verifying for correctness, that is you have some input specification, from the input specification you have developed the Verilog code, then you have transformed it by doing lot of optimization. So, transformation is very much required, that is you transform them and optimize them and so forth, and then before you feed it to your before you to high level synthesis tools, then what step is required? That is actually the verification tool, that is you have taken your tools, you have taken your CDFGs, you have taken your Verilog code, converted into CDFGs by doing all this transformation as we have seen. You may have given some inputs, outputs and debugged the code, and finally you said this code is ready. Now you can go for automated tool for high level synthesis, gate level synthesis and fabrication. But now you should be very careful here and you should go for verification, that it is you should verify formally that your specifications are equivalent or your specifications are all satisfied by the stuff you are delivering, because in the process of transforming your code, in the process of optimizing your code, you may sometimes lead to some kind of issues which may lead to a specification violation. A very simple example I just told in the answer is, sometimes we may put some kind of a dead computation to increase the length of a loop, because sometimes we may find out we may give a loop which has to be delay synchronized with some other stuff. Now for that you might have put some dead code so that the delay gets unnecessarily increased, or sleep kind of a thing in C language. But now because with transformation if you remove the code, then the delay will be decreased and there will be synchronization problem. So in such case, even if the transformation is there to optimize your code, but in this case because it may lead to non-synchronization and you may lead into problems. So therefore, before going for any type of transformation, debugging etc. and finally transforming your design, you should be very careful that there is no behavioral change from the specification. So that has to be verified, and formal techniques to do that we will be learning in the verification part of the module. And the next part of this course, that is next module, we will be looking at the CAD tools given what you call CDFG, which is optimized, correct, meeting specification etc. How to go for architectural design directly using kind of tools. So the algorithms required to do the conversion we will be looking in the next module. Thank you.